We on? I'm almost speechless. Before I get started, I want to put on this hat given to me by the LOC and SOC with this phrase, dare mighty things together. Thank you for this gift. It expresses my philosophy perfectly, and it certainly expresses JPL's philosophy. So thank you very much for bringing this along from Caltech and JPL. I'm going to put this on as a reminder that that's what we're all here to do. So that any celebration involves thanks, and I have many people to thank. Let's see if this.
Click on the screen first, like click with the mouse.
Oh.
And then try with the arrow.
Yes. First of all, to my family, to my students and postdocs over the many years, for all of your hard work, your inspiration, your dedication, and all of the organizing that you've put together in this meeting has taken me in many places, memories and very, very fond thoughts of how we worked together over the years. To Patricia, I probably wouldn't be here, as Rashid so glowingly told you, without her support and love. To mentors and teachers who have lit my path in many ways over the years. I will describe some of that as I go through my talk. To collaborators across the world, a number of you that are sitting in this room, for the just shared joy of working together on problems and the friendship that came from that in many, many instances. To Canada, where my family found a secure and wonderful home, and McMaster for the privilege of working here as a scientist and a scholar and a teacher for these many years. It's a privilege. And to the participants of Rolf Proposium for your this has been a great first-rate conference. I've been to many. This is really one of the best. And thank you very much for all your thoughts into this. So beginnings. My family is of Polish, comes from Poland of German ethnic origin. After the violence of World War II, my family reassembled in Germany, and my father, pictured here, Egon, was certainly not content to remain in Germany, and basically my mother came in 48, my father thereafter. This was taken in 1953 or 4. My brothers appeared on the scene. This is not James Dean. That's my uncle. The brother of my mother. Winnipeg was a very happy childhood experience for me, and my father took 2 semesters in engineering, or the war destroyed that, but he had a love of mathematics, architecture, and many things, and through both of our youth, we learned to play chess and do math years before the other kids could do that in school, and that continued as just an alert kid having a good time. But the moment I went into science was a moment that I can still picture of looking down at a slide of stained onion cells under a microscope that my friend had gotten as an award from his father's good salesmanship. It was an award for things that he got. This started me on a career in biology. I collected everything. I went everywhere, roamed around, got specimens, et cetera, et cetera. Went into science fairs. Winnipeg strongly encouraged that. So then we moved to Vancouver, and my grade 9 teacher, Mr. Sherman, took me aside as a very interested science kid and told me about experiments that had been done that had shown that RNA changed its composition in animals that had learned. So learning was associated with RNA. So here I am back 40 years ago, back in grade 9. But RNA has a different character for me now. And so I, of course, immediately started experiments on my own. So this is I won science, science fair awards, but here in high school, I've got an experiment set up in the back of the physics lab, actually, and doing experiments on this memory transfer idea. And I went to the university to use university labs as a high school student. I was employed there in a neuroscience lab, and I thought, that's where I'm going. I'm going to neuroscience when I go to university. Physics, rowing boats across streams and wind and this, calculate the vector. No, I took all those courses. No way. So university honors physics was my kiss off to physics. This was it. Just wanted to see what it was like. A change happened. That change was Eric Vogt, who is the co-instigator of the TRIUMPH facility, known to physicists around the world. He was known as his wonderful lecturer, and it's in his classes that I saw physics for the first time. And I thought, wow, this connected with my inner mathematical interests. And that was a conversion, although I still kept interest in neuroscience and worked as an undergraduate in neuroscience laboratories, but the course was set. At UBC, when I came back from Toronto with a master's degree in theoretical physics, I wanted a change. And my two PhD supervisors, first was Morris Price. You'll note he was a student of Max Born. I've taught a lot of quantum mechanics in this institution, and now I know why. Somehow I got that in the air, because Max Born, of course, was the famous father of so much in quantum mechanics. And it was Morris that put me onto accretion disks. I didn't know anything about astrophysics. I was just a theoretical physicist. I wanted to go in astrophysics. Morris said, accretion disks. This was in 1976. I came in 1972. The first theories of accretion disks were written down. Morris, because he was a wide-ranging, brilliant physicist, knew all about that. He took students all over in many different subjects and was willing to, he was interested in me going into an astrophysics problem of that kind. I read a few of the papers. That's all Morris really told me. Think about accretion disk and a few general ideas. And I just read that it seemed as if everybody blames things on the missing magnetic fields. We don't understand it. Maybe it's magnetic fields. That's where the paper ended. So I thought, maybe stupidly, I guess I have an opportunity here. So little did I know how hard that would be. And after 2 years, Morris retired. And Greg Fallman here, who became the director of the Hertzberg Institute, his generosity and brilliance in his own right as doing both observations, and he had been a theorist in Cambridge, worked in general relativity before he transitioned to observations, was my mentor until my PhD. But this was not the most important thing that happened to me at UBC. It was this. We heard about a person coming from Wichita, Kansas. Where is that? She was going to be a new student in astronomy. I was a physicist, but I had an office in astronomy. One day she walked across the campus and I, wow, what an interesting looking person. That person turned out to be lodged in my own office. It was like, okay, that's fantastic. So one thing happened after another, and we ended up going to Cambridge. When I graduated, she with no position, I with a McMaster postdoc, and away we went. So let me enter the question of how I got into star formation before I tell you some more details. My thesis back here, you'll note the topic of my thesis was dynamo action and accretion disks around black holes. X-ray astronomy was booming at the time. There were black hole sources suspected. That was Cygnus X1. There was X-ray shot noise from that. I thought one idea for explaining the X-ray variability was magnetic activity in the disk. Strong magnetic field generated perhaps dynamo action would generate these flares. That's where my thesis, that's what I thought was a good idea. And the mean magnetic field in this field would be driving accretion flows. I didn't think of it as accretion flows, but I did work out that mathematics. So when I went to Cambridge, it's because Martin Rees and his gang were hot on extragalactic radio sources and jets. And I thought that this, somehow what I was doing in my thesis must have some relation to this. And of the many theories available at the time, the two that struck me were this: galactic jets from spinning black holes. That's Roger Blanford and Znayak in '78. And they were just finishing their paper when I arrived in Cambridge on outflows from the disks around black holes. I thought that was very interesting. I'm a student. I went on my own as a postdoc. I'm not supervised by anyone in particular. I'm in a coffee room one day in Cambridge, and Colin Norman, who I'd gotten to know as a visitor from Amsterdam, told me outflows had been detected around young stars. This is the observational paper. It is L1551. Millimeter astronomy had just come on strong. This is the Planbeck, Snell, and Loren. And this is their outflow and how they conceived as the source of the outflow. No disks were really observed of any kind at that time. They have a decretion disk in this picture. Here's a CO outflow and a fast wind of some kind in the interior. This is the paper I read after Colin tipped me off. And we went forward very rapidly. One of the papers at Cambridge. The other one I worked at actually in Berkeley, where I did a second paper. And the third paper was at a JHU with Colin in 1986. And these became actually very famous papers. The next evolution was in Peltier and Pudritz. Guy Peltier was a brilliant plasma physicist. This was his introduction to astrophysics. I was there on leave paid by Grenoble. And in this work is the most mathematical, theoretical work I think even more than my thesis. We developed an entire analytic theory for how jets would develop. These very complicated nonlinear equations. After 3 years putting this together, before we published it, I realized then I could not do any more theoretical work on this. It's too complicated. They're highly nonlinear equations. Something had to give. And that's propelled me into McMaster to bumping in, or a very bright student appeared on my radar screen, recommended to me from leading French theorists. And I said, yes, that's my first graduate student. And he, Rashid Ziliyad, put together the idea of jets launched from the surface of accretion disk, doing this numerical calculation. Gratifyingly, the numerical calculations verified this basic picture, that an MHD wind from a disk, as we've heard many times in the meeting, if you imagine that you've got beads on a wire and you rotate that wire like this, you can imagine that if I tip that wire at a certain angle, the bead would fly off. The wire is a magnetic field line. The thing that's rotating is a disk that it's attached to. Gas is flung out as far as the alphane surface here. So I start here, I end here. There's a lever arm, or A over R0 turns out to be about 3 in numerical and theoretical stuff. This is Archimedes, basically. You have a lever arm in a problem. The amount of accretion that you get driven in because you're taking the angular momentum out is just related to the square of this lever arm ratio. That's just Archimedes, basically. And these observations have been verified many times now in observations over the years. Very, very recently. Another fortunate circumstance. I managed to attract Sean Matt here as a thesis, as a postdoc. And to complete this problem of accretion flow coming into the star, you're still ending up at this point with Kepler flow. That is very, very fast. If that angular momentum transfers to the star, it will spin it up to break up in no time. There was no general solution for this known at the time, but we realized that if you take accretion falling onto this, bringing its angular momentum to it, wanting to spin up the star, but if you could drive a wind out driven by the accretion power you're losing, you take that angular momentum out in a stellar wind. And this also has this is very hard to measure observationally, but that was the idea. And that perfectly mirrors current theory of black hole jets. Roger Blanford, in a review last few years, emphasized the jet from a black hole comes directed from the spinning hole, but that is supported by an outflow that surrounds it from a disk. So there's a symmetry between AGNs and protostars that goes very, very deep in this basic physics picture. And these are simulations, the state-of-the-art simulations, in a paper with Jan Stapp, who was Rashid's student, I believe. This is the highest resolution simulation of a jet, and still in the literature, I believe. And it shows a rotating jet surrounded by these toroidal magnetic field lines. which collimate the jet, just as in a tokamak. This took 40 years to verify. I can't tell you the feelings I've had about having ALMA now come along, and the illustration to me, very graphically, the importance of advances in technical advances in astronomy. Building new telescopes gives new results, period. So here are ALMA's observations of a molecular outflow now that's rotating around this axis. Here's the blue and red shift, the lobes telling you it's a signature rotation. These are molecular outflows. It used to be thought molecular outflows were purely the consequence of entrained gas that's been sucked up by the jet. No longer true. We now know that molecular hydrogen gets dragged out of jets and out to tens of parsec scales. This is the best observation that I know of for very high resolution work done here with a VLBA. Resolution scale of 0.05 AU. You're seeing major spots here being accelerated and following a helical trajectory outwards, just as if you were in a rotating flow that's moving outwards like that. This matches the theory perfectly. These are not my simulations, but of Oliva and Kuiper. So I leave this topic. Now the amazing good fortune of going next stop on my journey to Berkeley. Everybody wanted to go Berkeley in those days. I mean, that was like, the movies said that, astrophysics said that, that's where you wanted to go after years in a rainy England. Amazing. So here I encountered, this is for the Center of Star Formation and Interstellar Medium Studies. This was the picture that theorists labored on, led by Frank Hsu and his students, that star formation was a quiet affair. Magnetic fields are so strong that stuff just gradually leaks between magnetic field lines and you might get a collapse. There might be an outflow that clears things out. But this was always a very slowly regulated picture, okay? So then that Frank is down one floor from Chris's office. And this is what Chris is thinking about. Interstellar medium for Chris is this dynamic place. Supernovae create a hot phase in interstellar medium. It's completely turned over regularly by supernova activity. And so it's a very dynamic picture of the interstellar medium. How do these relate to one another? This only became apparent to me only rather later, the importance. These are spheres, but forget about that. Rachel just showed you some up-to-date pictures. This is Chris, his wife Suzanne, who is also the center of his life, just as Rashid told you about Patricia. And this is his student, Mark Krumholtz right over here. And Susanna Lozano was the star student in Frank's group. So moving on from there, at about that same time, this picture had come out. This is what inspired Jason and I. This is a map due to Elmegreen and Schneider and Elmegreen, of a globular filament. They took a catalog, hundreds and hundreds of pictures. This is just from a star catalog. Okay? This region here is obscured region of dust. You see it in white here. You see a filament and globs along this, more or less regularly spaced. This was in 1979. This is a very different picture. These things are connected. This is just a bunch of isolated blobs. So this became a talk that I saw in the late 80s by John Bally that brought this point up to me. Told me right away filaments was somehow something you wanted to work on. So let's go to McMaster now with my colleague and friend Bill. So after Berkeley and a sabbatical leave, I'm thinking, or before my sabbatical leave, I want to understand the properties of molecular clouds. This became Christine Wilson's supervisor, Nick Scoville. They had a survey of molecular cloud properties. I knew a lot about the ISM molecular by that time. And I was trying to understand what the distribution of masses of clusters in which clusters would form with molecular clouds. So I wandered down the hall thinking, Bill works on globular clusters. I wonder if there's some connection here. And Bill described that very well in his talk, that led to the idea that because there's a similar scaling between the mass functions of clusters right up to GMC masses and molecular clouds, that this is a unified picture of cluster formation across all scales, which has turned out to be pretty accurate. What do filaments have to do with star formation then? I think I'm going rather slow here, but just give me some time, just indicate. So the turbulent picture, the dynamic picture of star formation that came in the 90s with the advent of computers showed you that the inertial medium is supersonic. That creates shocks and filaments, and within those you could have star formation. So a huge advance in computers enabled this picture, and the theoretical work that went into it started by Maclo and Klesson, and there's basic papers here, including Chris's work, which point out that you can get the distribution of stellar masses by just using the distribution of density properties of a turbulent field. Okay, so turbulence and stars go together intimately. But that left aside the question, what about filaments? How does that fit into this picture? So what about star formation in filaments? We see structure and fragmentation, and later Helen Kirk was a postdoc with me. And here you have something that looks quite different. A filament would certainly be created in shocks and turbulence, but if, we have flows along filaments. We have structure developing here that's very specific. Rachel talked about this in her talk. So this set of ideas then led to appearance of Jason Figa. There's a lot of things I've worked on in my life, and there's many students I'm not talking about here, equally important. I'm just trying to create a thread through this bewildering array of things that I've worked on. But I'm trying to mainline, show you a direct main highway through the path here. So here in Jason's calculations in his PhD is one calculation here showing the fragmentation of a cylinder. This is supposed to be infinite. You see a velocity field that's created in this linear case. So this velocity field you see accelerating material into the central object here looks quite different than the predictions in the shoe theory of star formation. This is now a testable thread that we can do. So the fragmentation mass, if the mass per unit length for this hypothesized infinite long uniform cylinder is greater than critical value, you get fragmentation. And in the fastest mode that you might have is that the fragment scaling is periodic. It matches some of the observations. But it's this picture, observationally, that put this on the observational map. This picture is observation showing the white here is filaments that have higher than this critical mass. And the purple dots are where stars are forming. Red is below this critical. That's mass per unit length that's below that critical value. And these observations showed that fragmentation stars are forming in a region where you're above this critical mass. So now we have the start of a theory that's based on both turbulence and filament fragmentation. And recent observations show how beautiful this periodic structure is. Here in the California filament, this beautiful regular spacing, which can be accounted for in a theoretical picture like this. So in the work of Corey Howard that Bill mentioned, the last stage, we did numerical simulations of formation of clusters and filaments. I was bothered by the fact that we still assumed we were starting from something, a sphere. In Chris's conference, there's a lot of discussion about the McKee sphere. McKee spheres can be applied to almost any piece of astrophysics, and you'll get the answer right to about a factor of 3, whatever you do. Virial theorem, et cetera. It's haunting, but nevertheless true. This sphere is detached from its environment. That can't be true. These are embedded in the galaxy. There's flows onto filaments and the GMCs. So GMC is also not an isolated object. And so that motivated the jump into galactic simulations. These simulations are made possible by my colleague, James Wadsley there. Initial conditions and taken from his work. and applied for us in our paper together. And this simulation is a multi-scale zoom simulation from scale of a galaxy. You run this forward, pick up a box here, you will resolve more highly. Don't disconnect yourself from the background, for God's sake. Keep that derefined to some degree. Come down to a 3kpc box. Resolve in here. That's a molecular cloud box like it. Blow that up, and you will find that this fragmentation picture predicts that GMCs are forming out of many kiloparsec filaments, perhaps by fragmentation, separation of hundreds of parsec. And if you look on the smaller scale, the fragments that produce clusters are separated by about 14 parsecs, and they have that kind of fragment mass. This roughly corresponds to observations, although many more details are needed. My link to planet formation, I'll talk about in a moment. But this now is a modern picture of how we see where protostars are forming in the Orion, the nearby region of massive star formation, the Orion cloud. That's a cloud that's in the tip of the sword of the Orion Nebula, if you look there. And you will see that looking at where the protostars, these are blue and white magnetopoints, you can see them spread along this filaments that make up the molecular cloud. And this suggests if we could only zoom in, from the galaxy to that cloud and then down into the star, we'd have a whole picture. So that is what's motivating our current work. And just to see the connection with planet formation, these disks around these stars rapidly get depleted of the dust within the disk. So here are different clouds. This is the mass of the cloud, the amount of dust that it has at different clouds of different ages. And you can see for clouds that are more than about 3 million years, the dust masses you have available might be only less than 10 Earth masses. Jupiter has about 10 Earth masses of material in its core. When you drop below that, you can no longer make Jupiter. This observation shows that disks the lifetime of disks means that Jupiters have to form within a few million years, or it's impossible. This is the connection then between star formation and planet formation initial conditions. I'm going to speed up here a little bit, but just to say that the current group, there's Rachel here. These are my planet formation people. And Erica are involved in these zooming in finally to protoplanetary disk scales. Hopefully Rachel's thesis might get to that scale. In planet formation, I, again, fairly soon after we started in 2000, decided on trying to do something rather ambitious a decade later. So my current goal is to connect protoplanetary disk formation with exoplanet population. So here's what the problem is. Here is a theorist's view that's very accurate about the observations of what a protoplanetary disk looks like. Dust to a radius of about 1/10 of an AU here. It's too hot in the interior disk. Dust would melt inside this region here from the heat from the central star. 1 AU is where the Earth is. Jupiter is out here. And the evolution of this system and how it forms planets presumably has a lot of input to what we see in the distribution of planetary masses and what their orbit is. Here, here's the MA diagram showing you where hot Jupiters are, sub-Neptunes, which we've heard a lot of here, et cetera. So how do you go from here to here? Also accounting for the makeup of these planets. Are they icy? Are they rocky? What are they? Soko Matsumura started this when I made the shift. I always go into problems. I like exploring a problem freshly. I regard myself as a postdoc when I start a new problem. And I like to work very much with graduate students as part of that process of discovery. And so Soko was the student. She was very interested in planets, so we went that way at that time. I won't say more about radius values, but this turns out to be an excellent testing ground for theories of how planets are built. I won't say more. You've heard about this from a number of Ryan's students and Ryan himself. If you look at the mass-radius relation for planets, it's the radius of a planet, here's their mass. You see a lot of planets line up on this rocky world line, the same composition and structure as the Earth, up to about 25 Earth masses, and then nothing. Why is that? That touches a point that Farzana made in her talk, that the pebble isolation mass, that mass at which you shut off pebble flow onto yourself, is about 25 Earth masses. So this data may be an indication that the pebble isolation mass really is a real thing at controlling how massive the rocky worlds can become. There's a second sector here, which is taking off into this mini Neptunes and above, in which water, volatiles, and helium-hydrogen atmospheres will start to play a very large role in determining their structure and mass. We talked a lot about dust processes. I won't go there, but these observations, this is the best shot we have at the structure of this. This is again from ALMA, and this is the possible variety of ring and asymmetric structures in the ALMA data. And as Atesh said, are these the results of planets? Are planets forming in those rings? What gave rise to those rings if they are not planet-produced? We have now an excellent data that can control the dynamics of this. We know the velocities, the local densities, the intensities. So this is an excellent data set for which you can really start tuning the question, how are planets formed? Jess Speedy is already famous for work on demonstrating spiral waves are possible in the most massive disks here, indicating that planets can drive some of this structure. But does it drive all of it? So that's, maybe I could just say the second thing about planet formation is that planets must migrate. The problem was indicated by a McMaster graduate, Scott Tremaine. Scott and Goldreich showed that this Lindblad torque, when you have waves that are set off by a planet to a planet disk interaction, waves get propagated, the torque from those waves push a planet inward. They should be lost in 100,000 years. This is a torque map of such a disk. Red indicates motion inwards. This is disk radius. This is planet mass, how much torque you get on a planet located at that position. This pink line here shows you where you transition to the condition where you will open a gap and stop that rapid motion. Otherwise, the planet slips through when it's in its low mass state. What's the solution to this? One solution was proposed by, is the idea of just slowing it down by some unknown physics mechanism. Ida and Lin showed that you need to slow this rate by a factor of 30. So this again seemed to me a prime physics problem. How do you do that? How do you put that in models? One solution is to notice that very close to the planet, the density fluctuations, temperature fluctuations there also lead to exchange of angular momentum with the planet and that fluctuation. That leads to a co-rotation torque, which happens right near the planet. And that can drive outward migration. And here, just as plotted in our paper, the outward directed torque. Dark blue is a peak in the torque. If you add these two together, you'll find zero torque conditions, which is at ice lines, heat traps, density, and dead zones, which become planet traps. And that's the solution that we pose to this problem, that will be dynamical traps in the disk, which would stop planets, not just the dust. In opening a gap, the traditional picture, if you have turbulence in disks, is that you're fighting. So now I'm in this type 2 phase up here, high planet mass, where you open a gap. Maybe that's responsible for the gaps we see. You're fighting the planet torque, pushes transfer angular momentum from the inner to the outer disk. So it opens the gap. Viscosity, things spread in a viscous medium. So gas spreads back into the gap you're trying to open. But finally, there's a mass that's sufficient to force open a gap. That's up in here. If you have an MHD disk wind, that's a different question now. Because now you have an MHD-driven accretion flow through here that becomes, the magnetic field lines will now get concentrated in these gaps. And so now you're pushing against this advection flow driven by the MHD wind and opening that. That gives you a different criterion for gap opening. That's just one of the many examples where disk wind theory will fundamentally change planet formation ideas, such as this. This is from Ioma and yeah, sorry. I think I missed a reference. So it's right there. So how do you form disks? Again, in the Berkeley world, with the classical star formation theory developed many years ago that I learned from, that we all learned from, you had it that you had rotating pieces of gas that collapsed, the disk would inevitably be left behind, and that's how you form the system. But in a turbulent medium, that's not so. In a turbulent medium, you've got filaments of gas racing one another. And you look at a piece of gas and you say, what's the angle local, in that frame, what is the angular momentum of the filaments that are flowing my direction? If you do that, then you see the origin of disks is a chaotic affair. In these calculations, Daniel Seyfried and myself, and from the Heidelberg group, many filaments are converging here on formation of this filament. There's a Kepler disk inside, but it's joined by many filaments bringing in gas. Fast forward a decade, this is Michael Kuffmeyer's work, showing that even in late stages, where you've got a well-formed disk, well on its way to forming planets, there are now observed 1,000 AU streamers that are bringing in fresh material that can completely charge this disk again. Bringing maybe new material to form new planets in it. Here is touching Atesh's talk now. And this is where my center of mental gravity, one of my centers of mental gravity is now with my group. So if we want to form planets, the rings being produced by MHD processes. So here in this simulation, you see Riolzin having these regions of evacuated regions with magnetic flux in here. Wind is coming off most strongly from these regions, evacuating these cavities. This presumably should be a place where planets could form in these rings. JWST observations, just a few months ago, Francesca Bacciotti worked on this topic many years. Finally using ALMA observations, I believe these are, I think these are ALMA, sorry, showed that the outflows from HL tau, the famous ring system, are layered. It's like cones within cones within cones, where emission peaks. And if you take those cones back to the source in HL tau, they line up with some of the rings. A connection is made. So this is the way we're headed theoretically now. To understand, can we build up rings built by MHD instabilities that get dense enough to have to kick off planetesimal formation? It's by no means clear that that's achievable, but that's Atesh's thesis. And I think I'm running wildly over time here. So you'll have to collar me at this stage, but it's not too many more slides. The chemistry of disks now, what makes up the composition of disks. If you look here, the data for the composition of this, using JWST observations, now we finally have some idea of the chemical properties of disks around low mass stars, presumably it form M stars, and ordinary stars that will related to solar-like stars. The chemistry is different. The chemistry of this disk is high in reducing species here. That's this, you see hydrocarbon molecules, C2H2, rich in carbon species, CH4, in low mass disks, and you don't see them, you see that more dominated by water in oxygenated species for high mass disks. What that means is that if you're forming terrestrial planets in these regions, low mass disks could have planets that are more carbon dominated. What is a carbon dominated planet? What would it look like? What would its chemistry be? Could you have life? Or would that be easier or harder? So I regard this as an amazing result of JWST, this chemical result that has something we really want to investigate in the future. Just to finish a little bit here, you can, Julie Inglis, my student for our handbook article here, just published, shows you how looking at spectra, you can determine the difference between the hydrogen-rich, the so-called reducing-rich disks from disks in which you have plenty of oxygen. So you look at the C to O ratio in your gas, and you calculate the spectrum that you will see in this infrared part of the spectrum. And you see that as you tuned your C to O ratio downwards, so dominated with oxygen here and less oxygen at the top, you'll see that your spectra changes quite noticeably. You can from CO2 type of species to CH4. So spectrally, observers can actually kind of determine what kind of disk chemistry these might be, which is very exciting. And in our own models, in our own calculations, Alex Cridland taking our planetary synthesis calculations forward that was discussed here, we find that observationally, there's a clear sequence. If you look at the C to O ratio for more and more massive systems, you'll see that there's a systematic kind of a main sequence, as we call it, in the C to O ratio, doing the detailed astrochemistry of our models and calculating what kind of C to O ratio the atmosphere of the planet gets. There's this clear sequence that depends a little bit on planetary mass. And maybe this is a way of identifying where in the planet, where in the disk that planet came from. I'm going to transition now to origins of life because I've talked about hydrogen-rich things. Hydrogen cyanide is the basic feed molecule for building biomolecules. I'm making a big jump in chemistry now. But if you change, in this calculations here, if you change the chemical potential of oxygen, that's called the fugacity. If you pan through that, this is the kind of atmospheres and structure of the mantles you'll be getting, the species that dominate. As you go from low oxygen fugacity, you're dominated by methane, remember that? And over here, you'll get a CO2 type of atmosphere with high chemical potential. So this sets the stage for asking, is a planet inhabited? I view a planet as being inhabited if you can make biomolecules, you can make polymers like RNA. If that's a reasonable hypothesis, then worlds like this are not favored, whereas those conditions would be, for the reason I'm going to get into. And that now takes me to the, well, this is a roadmap for how I see the progress in planet formation theory, and it's basically rewriting the book, except using disk winds instead of traditional Shakura-Sunyaev viscosity in your calculations. And so the disk angular momentum, it's flowing out in the disk wind. It drives the accretion rates that you see. Because the disk is not turbulent, it's quiet, that's a good place to build up larger bodies in the dust that you need to make planets. Maybe the first planetary embryos are in the dust rings, in these MHD rings. We do not know that yet. We're trying to calculate that. The migration rates are determined by these wind torques, et cetera. So I call this a new paradigm for planet formation. Origins of life. Maybe this is the most interesting part for you, but my interest in this arose out of the fact that I was asked to chair Canada's first comprehensive decadal review for astronomy and astrophysics. I was asked to do this in 1997, and this forced myself and my committee. I was the chair. Bill here was a member of the committee. We had a couple of Americans on that, a 7-member team. And for the first time, we put together a very broad-ranging view of problem-oriented astronomy, multi-wavelength astronomy, which is a big change in the Canadian picture, which had always been, which wavelengths do we want to build next? Is it going to be optical telescope or a radio telescope? This picture I gained from being a postdoc in Berkeley. I very well remember sitting in McKee's and in Chris's lunchroom where we met on Mondays to talk about theory and all kinds of things. In the 80s, it was the field report for astronomy from the National Academy of Sciences that had this very broad perspective on things. And I thought, I didn't realize at the time, but I absorbed that as a way to think about astronomy as a whole. And so our committee very much took this tack, proposed ALMA and JWST as at the highest priority for space and ground-based instrumentation with entry into TMT and SKA, the Planck satellite. Fortunately, politics was on our side. We had a liberal government in place at the time. The prime minister, who became the prime minister, was the finance minister. They loved it. That started the project. And that was also coming back to McMaster. After all that occurred, seeing astronomy writ large as a multidisciplinary discipline, that I asked myself the question, couldn't we do something like this at a university? We've got all kinds of experts across all kinds of fields. Why can't we talk together and create something new? That was the Origins Institute. This slide is what made me realize that I, as a physicist, could do something about this big question. Because at the beginning of the century, a Soviet physicist and an English biochemist together put the idea that life origin has to do with the basic laws of chemistry and physics, using Darwin's idea of evolution. They immediately split the field into two possibilities, one driven by information first, and the other driven by metabolism networks, which Paul Higgs just talked about. As a physicist, I see this is the first thing that came to my mind as with RNA as a catalyst and information molecule. I won't go into this. I'm putting up this slide. Do not read this. These are the very basic components of RNA and DNA. Just want to show the reactions that give rise to these nucleobases. If you lead down the list, you can see that hydrogen cyanide is always there. 5 hydrogen cyanides together can make one adenine. It's unbelievable that our genetic material can be built up starting with hydrogen cyanide. It's a reason why it's a very, very poisonous gas, because it reacts so readily. So Ben has already discussed this, but what we wanted to know, Ben was my first, so far only PhD in astrobiology and origins of life. But we here as a team put together with ourselves and the Max Planck Institute, Thomas Henning, and put together their time-dependent chemical evolution codes with the code that Ben wrote to follow hydrogen cyanide chemistry. And we could ask the question, what is the fate in a warm little pond environment? What happens to nucleobases on a warm surface of a planet? Came up with a very general picture, which we calculated to death. Ben calculated to death, and also the student on the other side doing the time-dependent chemical models. But here is a picture then of a prebiotic world in which you've got a few ponds around, material maybe dropping into it from meteorites, et cetera, et cetera. If you make molecules like this, you can destroy them by hydrolysis, or when a pond evaporates by ultraviolet radiation, which destroys them. Against these sinks, you have polymerization in wet-dry cycles. To form a bond, you need to remove water. That happens when you can have a dry state. And so this warm-dry cycles seem to play a very important role in making possible polymers. I'm almost at the end. The yields for those calculations were quite small. It's like a delta function spike of these molecules you make in a pond, but you can't keep them there for more than 100 years. For a lasting, sustained input of making molecules, we go back to Stanley Miller. In Stanley Miller's experiments, which I think you all are aware of, you cook up an atmosphere that looks like Jupiter, very rich in ammonia species, et cetera. And in this reducing atmosphere, you pass an energy agent through it, lightning, and you'll create amino acids and nucleobases after only a day runtime. If you change your atmosphere to something oxidizing, it no longer works. What you're making in this process, the excitation produces hydrogen cyanide. How does this happen on a planet? On a planet, you have UV radiation shining down onto you. So how you make hydrogen cyanide is you start with methane, and nitrogen. Nitrogen, these are radiation, breaks these up into radicals, reactive radicals. They find one another and react to produce hydrogen in various kinds of species, including hydrogen cyanide. The main source for this then is how are you making methane? Here by undersea vents coming up, you keep the planet in a high hydrogen state by impacts here. You have the reaction of iron with water releasing hydrogen. So you keep your atmosphere reducing and you pump hydrogen, you pump methane into that, and you can produce, as Ben talked to us, relevant amounts of hydrogen cyanide. This plot only shows, if you follow these two lines, the purple and magenta, the hydrogen cyanide level always tracks the methane level. So the main problem you face in these atmospheres is how do you sustain methane? And that is an interesting problem I could bore you to death with for yet another lecture or so. I'll skip this, but the main points that we come down to are comparing the delivery in situ with making things in atmospheres. The key molecule here is methane, and as the driver of hydrogen cyanide, whereas in the planetary disks, you're making these molecules, you need hydrogen cyanide around that gets incorporated into your planetary bodies, into your planetesimals. The bottom line here is that all building blocks of RNA can be produced in warm little ponds from atmospheric hydrogen cyanide production. And this leads me just to the final couple of slides. Many of you have seen our Origins lab. It was clear to Ben and I that Ben had to calculate many cross-sections. He had to learn quantum chemistry from an outstanding theoretical chemist here, how to compute cross-sections to make the various reactions for a chemical network for hydrogen cyanide. Many of them didn't exist. We verified with a few experiments. You can imagine, not many laboratories specialize in hydrogen cyanide chemistry, right? I was to one, and there was a woman there I just regard as one of the greatest heroes I've seen, just operating there in a hydrogen cyanide environment completely competently. It was in Munich, actually. So here we've built a planet simulator to try to reproduce the kind of conditions in an early Earth conditions. Not here to make molecules, but the next stage to see how things might polymerize. The company that did that was Angstrom Engineering on designs, mainly Michael Ronstetter. I put a little bit of input into insisting that we build radiation sources here, so we can put in a spectrum of almost any kind, so that we could go to a Mars or conditions around another planet. So I returned to my youth. I have the privilege now to be at least a small part of a laboratory exercise. Our funding came through a CFI grant of support from the university. Michael is the PI for this. We're putting our first paper in, should be submitted this week on the first results of this. So 3 people in 3 different departments, bracing 2 different faculties, convinced deans that McMaster should put money into this, convinced the government this was a good idea, got $1 million to put this together, and we'll see what happens. But the importance of experiments in a field that's riddled with too much speculation and not enough calculation, I can't underestimate the importance of doing that. And Ben, after doing a brilliant theory thesis, decided to become an experimentalist. So here he is in Sarah Hurst's laboratory in JHU, and he's now built his own lab with his own students in Purdue who's going to pursue these questions of atmospheres. I conclude from this that I hope you see the connections between a galaxy and the origins of life. If you don't, I apologize. If you have a few glimmers, be assured that that glimmer is in my head, wherever that leads. And my students catch the bug as far as I can see. So it's just been tremendous fun. Ahead, I see what we want to do next on this frontier is to take this physics that we just showed you into the question, what's exo super Earths may be inhabited? And by that, I mean, what conditions are needed on those to make biomolecules, okay? And we've got the Habitable Worlds Observatory, which Yasuhiro is playing a big role in scientific guidance of, and his committees, in the future. So I'm looking forward to the appearance of that. I'm hoping I'm still going to be on this planet at that time. And with that, I thank you for your patience and all of your work. Thank you. Thank you. Thank you. That was quite an ovation. Thank you.
Shall we take a couple minutes for questions? If anyone has. All right.
Yes, that was a great talk, Ralph. I really appreciate you going over all your many accomplishments. My question was based on this comment that you made about whether there's only one origin of life. And in this pond picture where you have many ponds scattered around the Earth, you would think that there are a large number of places where life could arise. And so how come there's only one form of life that's made it here?
That's a great question in astrobiology. It really is. And I think the idea here is that, yes, there will be many such centers that do. You could not avoid that. Some of them may be successful in getting this RNA world that Paul talked about, which I think is the way things would go. Now you're in competing environments, right? So here I think Darwinism might kick in first. You know, the spread of molecules can be very rapid in winds, in ocean currents. The ocean wouldn't be a good idea, but rivers and rivulets connecting all of these ponds and a rising continent. These regions would, if you like, invade one another. And so I'm sure there's some intense competition that goes between life here, life 1.0 and life 1.1, and then Darwin takes over. And that could be very rapid. It only takes a few million years to get things circulated around the globe with current systems, you know. So I think this could be rather rapid to take over, and that all the data we have suggests the genetic code we know was already in place as far back as we can measure, like 3.5 billion years ago. We don't know about forehand. Our calculations suggest life would have occurred only 200 million years after the planet formed, because the fact that the Earth is known to become oxidized by 4.3, and that should kill things. So we would play, and I don't know what would have happened in the meantime. So how long this process took is a very interesting question, but I think it would be a competitive Darwin thing.
Yeah, I agree it would be competitive, but the result of Darwinian evolution after the formation of life is we have huge numbers of creatures. So
but they all have the same code.
Exactly, but why couldn't you have a huge number of codes?
Because probably, and this was Darwin's answer to your question, is that why doesn't life occur today? That was a basic question. If it can occur like this, why not now? It's just any kind of organic material is rapidly eaten by a living thing. So you can't start life today because the other life around it says, oh, there's lunch. That's it.
Sure. Yeah. I love that talk, Ralph. It was really awesome to see all the contributions across the broad fields over the years, and all the students that you've mentored. And my question is, you know, out of all those students, which one's your favorite?
Trick question, right? Let's just say every person in this universe is unique. We all have unique talents. And I always feel, you know, the image I have of in my group, I love jazz, as you know. And Miles Davis is one of my favorite jazz musicians. And what he did, if you look at his discography, his band changed regularly over the years. He was always at the forefront of jazz. But what Miles Davis always did, he had teenagers, the hottest young player on the block. Hire that guy, you know. It was the idea, and that could be anybody. And the idea was that the music went forward, and it's the individual players in the band that contributed. I mean, Miles had this picture, but it was the strength of a Herbie Hancock or a Ron Carter. They had their own individual voices. You can hear that in each of the bands. They change. And that's how I see a group. That's what I see myself doing. I'm not Miles Davis, but I see myself in that kind of a way of directing something, you know, that has a number of different components, all of which need to be added together to create music.
Okay. So Ralph, we have something very special for you next. We're going to transition to some concluding remarks.
Great.
I think, yeah, let's thank Ralph one more time.
Thank you.